Reality itself might be the greatest magic trick ever performed. We are about to embark on a journey to the edge of known physics, exploring 30 of the most profound quantum mysteries that could hold the keys to understanding everything from the violent birth of our cosmos to the very nature of your own conscious thoughts. By the end, you will see the universe not as a clockwork machine, but as a living, breathing puzzle of infinite possibility. We will investigate how a single particle can be in two places at once, and why looking at something might force it into existence. What single idea about reality are you most ready to have challenged? This foundational strangeness begins with a simple question: what is light made of? For centuries, scientists argued fiercely. Some, like Isaac Newton, believed light was a stream of tiny particles like miniature bullets. Others were convinced it was a wave like ripples spreading across a pond. Both sides had compelling evidence, and the debate seemed irreconcilable. Then, in the early 20th century, a series of experiments revealed something far more bizarre than anyone had imagined. Light, and indeed all matter, is both a particle and a wave. It does not choose one identity or the other. It exists in a ghostly state of both possibilities, a superposition, until something forces it to decide. The most famous demonstration of this is the double-slit experiment. Picture a barrier with two thin, parallel slits cut into it. Behind it is a screen that lights up when particles hit it. Now fire a stream of electrons one at a time at the barrier. You would expect each electron, being a solid little particle, to go through either the left slit or the right slit and create two neat bands of hits on the screen behind. But that is not what happens. As the electrons accumulate, they create a pattern of light and dark bands, an interference pattern. This is the unmistakable signature of a wave. A single electron, it seems, does not go through one slit. Its wave function goes through both slits simultaneously, interferes with itself, and determines where the particle version of itself will finally appear. The electron is in two places at once, exploring all possible paths. Now, here is where the mystery deepens into the realm of philosophy. What happens if you place a detector at the slits to see which path each electron actually takes? The moment you observe it, the interference pattern vanishes. You get two simple bands again. The act of measurement, of looking, collapses the wave function. The electron is forced to be a particle to pick a single path. It is as if the electron knows it is being watched. This leads to a staggering implication. At its most fundamental level, reality may not be a collection of definite things. It may be a shimmering cloud of probabilities, a set of potentialities that only snap into concrete existence when an observation is made. Think of it like a coin spinning in the air. While it spins, it is not heads and it is not tails. It is a superposition of both outcomes. Only when you catch it, when you make a measurement, does it become definitively one or the other. The quantum world suggests our universe is that spinning coin, and our conscious observation might be the act of catching it. This is not just about electrons in a lab. This wave-particle duality is the bedrock of all quantum mechanics. It is the first and most essential clue that the universe operates by rules far stranger than our everyday intuition can grasp. This leads us directly to the second and perhaps most iconic of our quantum mysteries. If a single particle can be in two places at once, what about an entire object? This is the principle of quantum superposition. A quantum system does not have to choose a single definite state. It can exist in a blend, a combination of all its possible states at the same time. The classic and admittedly bizarre illustration of this is the thought experiment known as Schrödinger's cat. Imagine a cat sealed inside a box with a diabolical device. The device contains a single radioactive atom. If the atom decays, it triggers a mechanism that releases poison, and the cat dies. If the atom does not decay, the cat lives. According to the rules of quantum mechanics, that radioactive atom is in a superposition. It has both decayed and not decayed simultaneously until someone opens the box and looks inside. Therefore, until that observation is made, the cat itself must also be in a superposition. It is, in a quantum sense, both alive and dead at the same time. Now, this seems absurd when applied to a fluffy household pet. Erwin Schrödinger proposed this thought experiment not to suggest cats have quantum immortality, but to highlight how strange the math of superposition becomes when scaled up to our familiar macroscopic world. It forces us to ask a profound question. Where does the quantum weirdness end and our solid, everyday reality begin? The answer is that superposition is not just a philosophical puzzle. It is a physical fact routinely observed in laboratories. Scientists can trap a single atom or a photon of light in a state of superposition, holding two contradictory realities in a delicate balance. They can send an electron spinning in two opposite directions at once. These are not hypotheticals. They are the bedrock of a technological revolution already underway. This is the magic behind quantum computing. A traditional computer bit is like a simple light switch. It can only be either a 0 or a 1. A quantum bit or qubit exploits superposition. It can be a 0, a 1, or crucially, a mixture of both 0 and 1 at the same time. This means a single qubit can hold more information than a classical bit. But the real power comes when you link multiple qubits together. Two classical bits can be in one of four possible combinations. Two qubits in superposition can be in all four of those combinations simultaneously. As you add more qubits, the number of simultaneous calculations explodes exponentially. A quantum computer with just 300 qubits in superposition could, in theory, perform more calculations in an instant than there are atoms in the known universe. It could model complex molecules for new medicines, crack encryption codes that would take classical computers billions of years, and simulate the universe itself in ways we can barely dream of. All because we have learned to harness the ghostly, simultaneous reality of superposition. So the next time you hear about Schrödinger's cat, remember it is more than a metaphor. It is a doorway to understanding a universe where possibility is not a future event, but a present and tangible state of being. But harnessing superposition is only the beginning of the quantum story. If you think a particle being in two places at once is strange, wait until you meet its entangled twin. This is the phenomenon that so disturbed Albert Einstein he famously called it spooky action at a distance. Imagine you create two particles together, perhaps two photons of light, in such a way that their properties become perfectly linked or entangled. You could separate them by any distance you like, sending one to a lab on Earth and the other to a probe near Mars. According to quantum mechanics, these particles do not have definite, individual states. They exist in a shared, blurred reality. Their properties, like their spin or polarization, are correlated but undecided. Now, here is the spooky part. The moment you measure one particle, forcing its property to snap into a specific value, the other particle's corresponding property instantly snaps into the opposite value, no matter how far apart they are. It is as if the second particle receives a message at infinite speed, violating the cosmic speed limit set by light. Einstein hated this idea. He believed it pointed to a flaw in quantum theory, suggesting there must be hidden variables, predetermined instructions the particles carried with them from the moment of their creation. For decades, this was a philosophical debate. Then, in the 1960s, physicist John Bell devised a way to test it. Bell's theorem created a mathematical inequality. If hidden variables were real, the results of certain entangled particle measurements would stay within a specific limit. If quantum mechanics was correct and the particles were truly connected non-locally, the results would violate that limit. Experiments were conducted and the results were unequivocal. Bell's inequality was shattered. the particles were communicating, or rather, acting as a single entity in a way that no local hidden variable theory could explain. Spooky action was real. This confirmation of quantum entanglement is not just a laboratory curiosity. It is the foundation for quantum technologies that sound like science fiction. The most advanced is quantum cryptography, or more precisely, quantum key distribution. Because measuring an entangled particle disturbs it, any attempt to eavesdrop on a quantum communication channel is immediately detectable. You could send an encryption key encoded in the states of entangled photons. If a spy intercepts even one photon to read its state, the entanglement is broken, and the legitimate users know their line is no longer secure. It promises a future of perfectly unhackable communication. But the deepest implication of entanglement is a direct assault on our classical understanding of the universe. It suggests that at a fundamental level, space itself might be an illusion. Two particles can be light years apart, yet they are not truly separate. They are part of a single, unified quantum system. This non-locality hints that the fabric of reality is deeply interconnected in ways we are only beginning to fathom, weaving a web of instantaneous links that defies our very notion of distance and time. Entanglement shatters our idea of distance, but it leads to an even more unsettling question. What force decides when the quantum dice finally stop rolling? This is the infamous measurement problem, the deepest philosophical wound at the heart of quantum mechanics. We know that particles exist in ghostly superpositions, and we know that the act of observation makes those possibilities vanish, leaving behind a single, concrete fact. But what, in the universe, actually counts as an observation? Where is the line between the fuzzy quantum realm and our definite classical world? The standard textbook answer is called the Copenhagen interpretation, championed by pioneers like Niels Bohr and Werner Heisenberg. It takes a pragmatic, almost agnostic stance. It says, do not ask what is happening before you look. The mathematics of the wave function is just a tool for calculating probabilities. The collapse into reality is a fundamental, irreducible process that happens whenever a quantum system interacts with a macroscopic measuring device. In this view, the measuring apparatus itself, like a Geiger counter clicking or a photographic plate developing a dot, is what causes the collapse. Consciousness is not required. It is a chain reaction from the quantum to the classical, but this has always felt like a hand wave to many physicists. It simply defines the problem away by saying measurement is what measurement does. If the universe is fundamentally quantum, why should big things be different from small things? This dissatisfaction spawned other, far more radical interpretations. The most mind-bending of all is the many worlds interpretation proposed by Hugh Everett in the 1950s. Everett took the mathematics of quantum mechanics with absolute seriousness. He said the wave function never collapses, not ever. Instead, every possible outcome of a quantum event actually happens, but in a newly branched parallel universe. In this view, when you open Schrödinger's box, you do not find a cat that is either alive or dead. The universe splits in two. In one branch, you see a live cat and celebrate. In another, completely separate but equally real branch, you see a dead cat and grieve. There is no single outcome. There is only the branching tree of all possibilities, with every version of you experiencing a different result. This interpretation elegantly removes the need for a special collapse rule, but at the cost of proposing a near infinity of unseen worlds. Then there is the most provocative idea of all. What if the observer is not just a machine but a conscious mind? This suggests that consciousness itself is the trigger that collapses the wave function. In this view, reality remains in a state of potential until a conscious being perceives it. The universe, in a very literal sense, requires a witness to bring it into being. This idea, while controversial and bordering on the mystical, is taken seriously by some prominent thinkers because it places our inner experience at the center of the cosmic puzzle. It directly links the mystery of quantum mechanics to the mystery of the mind. Are we passive observers of a pre-existing world, or are we active participants in its creation? The measurement problem has no agreed-upon solution. It stands as a stark reminder that we have discovered the rules of the quantum game, but we still have no idea who the player is or even what the board looks like. The act of looking may be the most powerful and least understood force in the universe. If observation can freeze reality, does time itself depend on being watched? This is the startling territory of the quantum Zeno effect, named after an ancient Greek philosopher's paradox about motion. The principle is deceptively simple yet utterly counterintuitive. An unstable quantum system, like a radioactive atom poised to decay, evolves and changes over time. But if you observe it continuously, you can actually stop that change from happening. It is as though the constant scrutiny pins the system in place, preventing it from transitioning to another state. The atom is caught, frozen by the gaze of the observer. This is not merely a theoretical quirk. It has been demonstrated in laboratories. In one classic experiment, scientists used lasers to constantly monitor the quantum states of beryllium atoms trapped by electromagnetic fields. By repeatedly and rapidly measuring whether the atoms were in a particular energy state, they dramatically slowed the rate at which the atoms could transition out of that state. The more frequent the observations, the more effectively the atoms were held in place. Think of it like repeatedly checking a pot of water to see if it is boiling. Each time you lift the lid, you let heat escape, delaying the moment the water actually reaches a rolling boil. In the quantum world, the act of measurement is not passive. It is an intervention that resets the clock. Every observation collapses the wave function back to its initial state, forcing the system to start its evolution all over again. Under constant observation, it never gets the uninterrupted time needed to complete a transition. It is perpetually stuck at the starting line. This leads to a profound and almost mystical implication. Change, the very flow of time at the quantum level, may not be an inevitable, relentless force. It appears to be fragile, something that requires periods of unobserved freedom to proceed. What we perceive as the steady tick of a clock emerges from a substrate where time can be suspended by attention. Could it be that reality, in its most basic form, is not a continuous movie but a series of frozen frames, and only when we look away does the film advance to the next frame? The quantum Zeno effect suggests that our interaction with the world is not a one-way street. We are not just reading the book of the universe. By the mere act of looking, we might be holding certain pages open, preventing the story from turning. The quantum world is a place where barriers are not always what they seem. A particle confined within an energy well, like an electron bound to an atom, faces a wall it classically cannot climb. It simply lacks the energy, like a marble trapped at the bottom of a bowl. Yet, inexplicably, it sometimes appears on the other side. This is not science fiction. This is quantum tunneling, the bizarre ability of particles to vanish from one side of an impassable barrier and reappear on the other, as if they dug a magical tunnel straight through. The explanation lies once again in the probabilistic, wave-like nature of reality. A particle is not a tiny, solid ball with a definite location. It is a cloud of probability. While most of that cloud is reflected by the barrier, a tiny portion of it always leaks through to the other side. There is a small but non-zero probability that the particle will simply be found there, having effectively teleported through a wall it could never surmount. This is not a rare or exotic event. It is happening right now, and it is the reason you exist. At the core of our sun, hydrogen nuclei must overcome a tremendous barrier of electrical repulsion to get close enough to fuse into helium and release the energy that lights our world. Individually, they do not have nearly enough heat or pressure to smash through that barrier. But thanks to quantum tunneling, there is always a chance, however slim, that a nucleus will simply tunnel through the repulsive force and fuse. The Sun is not a perfect fusion reactor. It is a quantum tunneling machine relying on this statistical magic to burn. Without it, stars would be dark, and the universe would be devoid of the heavy elements that make up planets and life. This same principle is the silent engine inside many of your everyday devices. The tunnel diode, a cornerstone of early high-speed electronics, and the flash memory in your phone and computer both rely on electrons tunneling through thin, insulating layers to store and process information. The very act of reading this script involves trillions of tunneling events in the microscopic circuits of your device. So if particles can ignore solid barriers, could the universe itself contain hidden shortcuts? Some physicists speculate that quantum tunneling might not just be a mathematical quirk, but a physical glimpse into a deeper structure of reality. One radical theory suggests that tunneling could be evidence of extra, compact dimensions. In this view, a particle does not go through the barrier in our familiar three-dimensional space. Instead, it momentarily takes a detour through a higher dimensional shortcut, reappearing on the other side in a way that looks to us like magic. It is as if an ant trapped inside a closed loop of string could escape by briefly stepping off the string into the third dimension, then stepping back on at a different point. Could the universe be threaded with such hidden pathways, allowing matter and energy to bypass the normal constraints of space? While this remains speculative, it underscores a profound truth. Quantum tunneling reveals that the walls of our reality are porous, hinting that the solid world we perceive is built upon a foundation of endless possibility and escape. The walls of reality may be porous, but what about the space between them? What if the void itself is not empty at all? This brings us to one of the most profound and unsettling implications of quantum theory. According to quantum field theory, what we call empty space, the vacuum, is not a barren nothingness. It is a seething, bubbling ocean of energy, alive with fleeting activity. This is the mystery of vacuum energy, also called zero-point energy. The name comes from a simple quantum rule. Even at absolute zero, the theoretical temperature where all motion ceases, a quantum system retains a fundamental, irreducible jitter. Its energy never quite hits zero. There is always a residual hum, a vibration in the very fabric of existence. For empty space, this means that at scales far smaller than an atom, virtual particles are constantly flickering into and out of existence. Pairs of particles and their antiparticle opposites borrow energy from the vacuum for an unimaginably brief moment, allowed by the uncertainty principle, before annihilating each other and returning the energy loan. Space is not still. It is a quantum foam, a frenzy of creation and destruction happening everywhere all the time. We can actually witness the ghostly pressure of this quantum sea. This is the Casimir effect, a stunning experimental proof that the vacuum is alive. Imagine two perfectly smooth, uncharged metal plates placed extremely close together in a vacuum chamber, parallel to each other. In the classical world of Newton, with truly empty space between them, nothing should happen. But in our quantum reality, something remarkable occurs. The seething foam of virtual particles outside the plates includes all possible wavelengths. However, in the narrow gap between the plates, only certain wavelengths can fit, like specific musical notes resonating in a tiny chamber. This restriction means there are slightly fewer virtual particles, and thus less vacuum pressure pushing from inside the gap than there is pushing from the outside. The result, the plates are gently pushed together by the sheer pressure of nothingness. This minuscule force has been measured repeatedly in laboratories. It is not magnetism or gravity. It is the direct fingerprint of the universe's background energy, the tangible push of virtual reality. This discovery leads to perhaps the greatest numerical discrepancy in all of science, a puzzle so severe it is called the cosmological constant problem. If empty space contains this intrinsic energy, then it should exert a gravitational effect, According to Einstein's equations, energy in any form warps spacetime. So this vacuum energy should act as a kind of anti-gravity, a repulsive force causing the universe to expand. This is exactly what astronomers observe today. We call it dark energy, the mysterious force accelerating the expansion of the cosmos. The problem is one of scale, a catastrophic mismatch between prediction and observation. When physicists calculate the theoretical energy density of the quantum vacuum, based on the contributions of all known particle fields, the number they get is absurdly, unimaginably large. We are talking about a value that is 1 followed by 120 zeros times bigger than the amount of dark energy we actually measure in the universe. If the theoretical calculation were correct, the repulsive force of vacuum energy would have been so immense that it would have torn apart every atom, every nucleus in the first instant after the Big Bang. Stars, planets, and life would have been impossible. The cosmos would have blown itself apart before it even began. Yet here we are in a universe that is expanding, but at a remarkably gentle pace. Our reality exists in a breathtakingly narrow window between a vacuum energy so powerful it would destroy everything, and one so weak it would have allowed gravity to crush the universe back into a singularity long ago. Why is the observed value of dark energy so infinitesimally small, yet not quite zero? This is not a minor accounting error. It suggests our understanding of the quantum vacuum, or gravity, or both, is fundamentally incomplete. It hints that some deep, unknown symmetry or principle is cancelling out almost all of this background frenzy, leaving behind only the faintest whisper that now drives the fate of the entire cosmos. The silence of space, it turns out, is the loudest unsolved problem in physics. This seething quantum vacuum holds a secret that could unravel the very fabric of space and time. At the edge of a black hole, where gravity is so strong that not even light can escape, the rules of quantum mechanics and Einstein's theory of general relativity collide in a spectacular contradiction. This is the black hole information paradox, and it threatens a core principle of our universe. Quantum mechanics insists that information is sacred, never created or destroyed. If you burn a book, the information in its pages is not truly gone. In principle, a being with infinite knowledge could collect every particle of smoke and ash, trace every photon of light and ripple of heat, and reconstruct the entire book. The information is scrambled, but it persists. Now consider a black hole. According to Stephen Hawking's revolutionary work in the 1970s, black holes are not completely black. That frenetic quantum vacuum at the event horizon, the point of no return, allows for a bizarre escape. Normally, a particle-antiparticle pair flickers into existence and annihilates instantly. But if this happens right at the event horizon, one particle can fall in while the other escapes, stealing a tiny amount of the black hole's mass. To an outside observer, the black hole glows with a faint heat now called Hawking radiation. Over eons, this process causes the black hole to slowly evaporate, shrinking until it presumably vanishes in a final burst of energy. And here lies the paradox. The Hawking radiation that leaks out is random thermal noise, like the static from a hot stove. It carries no information about the specific stars, planets, or books that fell into the black hole. When the black hole is gone, all that unique information seems to have been erased from the universe, violating the fundamental quantum law. It is as if you burned that book and the ashes themselves dissolved into nothingness. This paradox led to an even more violent idea, the firewall paradox. If information must be preserved, perhaps it is not lost inside. Maybe it is violently released at the event horizon itself. The proposal suggests that instead of an empty space you could cross without noticing, the event horizon is a wall of blazing high-energy particles, a firewall that would incinerate anything trying to fall in. This solves the information problem by scrambling and releasing data at the boundary, but it creates another. It violates Einstein's principle that crossing the event horizon should be uneventful for the falling observer, a cornerstone of general relativity. So we are left with an impossible choice. Either quantum mechanics is wrong and information can be destroyed, or general relativity is wrong and black holes have deadly firewalls. Neither option is acceptable to physicists. The most promising escape from this trap is a concept so radical it reimagines the nature of reality. It is called the holographic principle. This idea suggests that all the information contained within a volume of space, like the interior of a black hole, is not spread throughout that three-dimensional volume. Instead, it is encoded on its two-dimensional boundary, the event horizon, like a cosmic DVD. Every particle that falls in leaves a kind of pixelated imprint on the surface. The three-dimensional world we experience, including the chaotic interior of the black hole, is a projection from that two-dimensional data, much like a hologram that appears three-dimensional but is generated from flat film. In this view, the information never actually falls into a singularity. It is smeared and stored on the horizon, and as the black hole evaporates via Hawking radiation, that information is slowly and chaotically leaked back out, scrambled but preserved. The holographic principle does more than solve a paradox. It hints that the universe itself might be a hologram, a lower dimensional reality that only appears to have depth. Your perception of being a three-dimensional being moving through three-dimensional space could be the ultimate illusion, a projection from a vast, flat information field at the edge of the cosmos. The fate of a single bit of information in a black hole may therefore decide the true nature of everything we see and touch. The holographic principle suggests our reality may be a projection, but what is the screen made of? This brings us to the single greatest unsolved problem in modern physics, the quest for a theory of quantum gravity. We have two magnificent, breathtakingly successful descriptions of the universe. Quantum mechanics governs the subatomic world, a realm of probability, particles, and discrete jumps. Einstein's general relativity describes the cosmos, a realm of smooth curves, gravitational fields, and the geometry of space-time itself. Each theory is spectacularly accurate in its own domain. Yet when they meet, they produce not a unified symphony, but a violent, screaming contradiction. The problem is that gravity, as described by relativity, simply refuses to be quantized. In the quantum world, forces are carried by particles. Electromagnetism has the photon. The strong nuclear force has gluons, but gravity's messenger particle, the hypothetical graviton, remains elusive. More critically, the mathematics of general relativity treats spacetime as a smooth, continuous fabric. Quantum mechanics insists that at the tiniest scales, everything is granular and jittery. When you try to apply quantum rules to gravity, the equations explode into infinities, producing nonsensical answers. This mathematical breakdown becomes physically catastrophic in two places, the centers of black holes and the first moment of the Big Bang. Both are singularities, points of infinite density where the smooth fabric of spacetime is predicted to tear. Physics as we know it stops. To understand the cosmos at its birth or the ultimate fate of matter, we must find a deeper theory that heals this rift. Two grand and very different visions have emerged as frontrunners. The first is string theory. It proposes that the fundamental ingredients of reality are not point-like particles, but unimaginably tiny, vibrating strings. Just as different vibrations on a violin string produce different musical notes, different vibrational patterns of these strings produce all the particles we see, from electrons to photons and, crucially, the graviton. In this view, gravity is woven into the music of the strings from the beginning. String theory requires a startling trade-off, however. For its mathematics to work, the universe must have more than the three spatial dimensions we experience. It needs extra dimensions, perhaps 6 or 7, curled up into shapes so small that we never notice them. The second major approach is loop quantum gravity. It takes a more direct path. Instead of adding new ingredients like strings, it focuses on quantizing space-time itself. In this theory, space is not smooth and continuous. It is woven from an immense network of tiny, discrete loops, a fabric of finite threads. Picture the universe as a vast cosmic tapestry. At the smallest scale, the fabric has a finite weave. There is a smallest possible unit of area and volume, a quantum of space. This granularity prevents the formation of true singularities, replacing the infinite point at the heart of a black hole with a dense but finite knot of space-time. Both theories are monumental intellectual achievements, yet both face immense challenges. String theory, while elegant, predicts a vast landscape of possible universes, making definitive predictions for our own universe difficult. Its extra dimensions remain unobserved. Loop quantum gravity provides a compelling picture of quantized space, but has struggled to fully incorporate other forces and matter in a unified way. The quest for quantum gravity is more than an academic exercise. It is a search for the operating system of reality. The moment we find it, we will finally have the language to ask and perhaps answer the most profound questions of all. What happened before the Big Bang? What lies at the center of a black hole? And what, in its truest essence, is the stage upon which the quantum drama unfolds? If our universe is a hologram, where is the film? The answer, according to the holographic principle, is that the film is all around us on the very boundary of everything we can see. This is not a metaphor about simulation, but a rigorous mathematical proposal born from the fiery paradox of black holes. It began with a surprising discovery about black hole thermodynamics. Physicists found that the entropy of a black hole, which measures its hidden information, is not proportional to its volume, as you might expect for a three-dimensional object. Instead, it is proportional to the area of its event horizon, its two-dimensional surface. A black hole's capacity for information is painted on its skin, not stuffed inside its belly. This bizarre fact suggested a radical possibility. What if all the information needed to describe everything within a volume of space, every star, every atom, every thought, could be perfectly encoded on its bounding surface with no loss of detail? The three-dimensional world would be like a holographic image projected from the two-dimensional data on the boundary, an illusion of depth generated from a flat code. The holographic principle found its most concrete form in a groundbreaking theoretical discovery called the anti-de Sitter conformal field theory correspondence, or AD-SCFT. It is a complex mathematical duality, but its essence is revolutionary. It demonstrates a perfect equivalence between two seemingly different universes. On one side is a universe with gravity, existing in a warped, bowl-shaped space called anti-de Sitter space. On the other side is a universe without gravity, described by a quantum field theory that lives on the flat, lower-dimensional boundary of that bowl. Every event, every particle interaction in the gravity-filled bowl has a precise, one-to-one translation as a complex interaction of quantum fields on the boundary. They are two descriptions of the same reality. This is a duality more profound than wave-particle duality. It says that a theory of gravity in a volume is completely equivalent to a quantum theory without gravity on its surface. One is the hologram of the other. Now, our actual universe is not an anti-de Sitter space. It is expanding and flat. But the power of the AD-SCFT correspondence is that it proves the holographic principle is mathematically sound. It shows that our intuitive sense that reality requires three dimensions might be a cognitive illusion, a useful fiction generated by a deeper, simpler, two-dimensional truth. This has staggering implications for the quest for quantum gravity. The greatest obstacle to unifying quantum mechanics and general relativity is that gravity, the geometry of space-time, seems so different from the other quantum forces. But if gravity is not fundamental, if it is an emergent phenomenon that arises from quantum information processing on a lower dimensional surface, then the problem simplifies dramatically. We would not need to quantize gravity itself. Instead, we would need to understand the quantum system on the boundary from which gravity and three-dimensional space naturally emerge, like the pattern of heat rising from a hot road creating the mirage of water. In this view, the Big Bang was not an explosion in space, but a transformation of information on a cosmic screen. A black hole is not a hole in space-time, but a dense patch of code on the universal hard drive. Your journey from one room to another is not a movement through empty space, but a change in the relationships between fundamental bits of information on the boundary of existence. The solidity of your hand, the vastness of the night sky, the flow of time itself, all might be a magnificent collective illusion, a story being told on the surface of a sphere we can never see. Yet this magnificent illusion requires a mechanism to make it feel real. How does the shimmering quantum world of possibilities solidify into the single, stubborn reality we all agree upon? The answer lies in a process as relentless as it is subtle: quantum decoherence. This is the quiet eraser of quantum magic, the reason Schrödinger's cat is never both alive and dead in our experience, and the bridge that connects the bizarre quantum realm to our familiar classical world. Decoherence explains how a quantum system loses its quantumness, its delicate superpositions and entanglements, simply by interacting with its environment. Consider a single electron in a pristine, isolated lab, perfectly in a superposition of spinning both clockwise and counterclockwise. This fragile state can be maintained as long as the electron is utterly alone. But the universe is never empty. Even in the best vacuum, the electron is bathed in the faint glow of starlight, the whisper of cosmic background radiation, the gentle tug of distant gravitational fields. The moment it interacts with a single stray photon, something fundamental changes. That photon becomes entangled with the electron. It carries away a tiny piece of information about the electron state. Now, to know the full quantum state of the electron, you would need to track down and measure that photon as well, and every other particle it has ever interacted with. This information bleeds out into the environment at the speed of light, becoming irretrievably scrambled. From the perspective of anyone trying to measure just the electron, the superposition is gone. It appears to have collapsed into a single, definite spin. Decoherence is not a theory of wave function collapse. It is a description of how quantum probabilities become effectively classical probabilities through interaction. It is why we never see tables and chairs in superpositions. They are constantly bombarded by trillions of air molecules and photons every second, their quantum states constantly measured and recorded by the environment around them. The world becomes definite not because a conscious observer looks, but because the universe is always looking, always measuring, through an endless storm of microscopic interactions. This presents a monumental challenge for one of our most ambitious technologies, the quantum computer. A qubit relies on maintaining superposition and entanglement to perform its magic. But if even a single particle from the outside world disturbs it, that qubit decoheres. Its delicate quantum state collapses into an ordinary classical bit, ruining the calculation. This is why quantum computers are engineering marvels of isolation. They operate at temperatures colder than deep space, shielded in elaborate vacuums, all to slow the inevitable tide of decoherence, to buy enough time for the quantum logic to complete. The race to build a practical quantum computer is in many ways a race against decoherence. Yet this same process may also hold a key to the deepest philosophical mystery, the measurement problem. If decoherence explains how superpositions become effectively classical through environmental interaction, does it eliminate the need for a conscious observer to collapse the wave function? Many physicists believe it does. In this view, there is no special moment of collapse. There is only the continuous, irreversible spreading of quantum correlations into the environment. What we call a measurement is simply the point at which a record of an event becomes stable and amplified enough for a human brain to register it. The universe does not need a mind to make it real. It makes itself real through endless conversation. However, a profound question remains. Decoherence explains why we see only one outcome, but does it explain why that particular outcome was chosen? The mathematics of decoherence shows the fading of the interference patterns between possibilities, leaving behind only classical probabilities. But it does not, by itself, select a single, actualized history. Some interpretations, like the many worlds view, embrace this. They say every possibility encoded in those probabilities does actualize, but in branching, decohered worlds that can no longer interfere with each other. From inside any one branch, it simply looks like one thing happened. So decoherence may not be the full answer to the measurement problem, but it is the essential mechanism that makes the problem tangible. It is the process that transforms the quantum symphony of maybe into the classical click of yes or no, building the solid ground of our reality from a sea of fading echoes. Decoherence builds the solid ground of our present moment, but what if that ground is not moving forward at all? This leads us to a mystery that strikes at the very heart of our experience. What is time? We feel its relentless flow, the irreversible arrow from past to future, the ticking clock of our lives. Yet in our most fundamental theories of the universe, time might not exist as a fundamental ingredient. It could be a magnificent illusion, an emergent property that arises from something deeper. This is the notorious problem of time in quantum gravity. When physicists attempt to merge general relativity with quantum mechanics, time often vanishes from the equations entirely. The most famous example is the Wheeler-DeWitt equation, a cornerstone of quantum cosmology. This equation describes the entire universe as a quantum object, but it contains no time variable. It is a timeless snapshot, a frozen picture of all possible configurations of space and matter. It is as if the universe is a single, unchanging block, and our journey through it is just a reading of different pages in a book that already exists cover to cover. This presents a paradox so severe it is called the problem of time. If our most basic equations are timeless, where does our powerful, visceral experience of time's flow come from? How do we get change from a picture that does not change? One compelling answer suggests that time emerges from quantum entanglement. Think of the universe as a vast, interconnected quantum system. As different parts of this system become entangled, they exchange information. The order in which these correlations form creates a sequence, a kind of cosmic clock. Your perception of time flowing from one moment to the next could be the result of you, as a subsystem, becoming entangled with your environment in an irreversible way. In this view, time is not a river flowing past us. It is a thermodynamic or statistical phenomenon, a side effect of increasing quantum disorder, much like the way heat spreads from a warm cup to a cold room. The arrow of time points in the direction of increasing entanglement, from a state of low correlation to a state of high correlation. This explains why we remember the past but not the future. The past is a state where correlations have been established and recorded in the environment like footprints in sand. The future is a state of potential correlations not yet fixed. This entanglement-based time also provides a stunning link to black holes. A black hole's event horizon is a surface of maximum entanglement with the outside universe. Some theories propose that the passage of time for an observer outside a black hole is generated by their increasing entanglement with the radiation and particles emanating from it. Time in this radical picture is not a backdrop. It is a story told by relationships. It is the narrative woven by particles becoming intertwined, by information spreading, by the universe gradually remembering itself. Your now is not a point on a pre-existing line. It is the leading edge of a wave of correlation, a moment of becoming real through connection. So the next time you glance at a clock, consider this. You are not measuring a fundamental force of nature. You might be witnessing the universe in all its quantum complexity, learning how to tell its own story. The idea that time emerges from entanglement suggests a universe built on connection, and nowhere is this connection more elegantly exploited than within life itself. For decades, biology was considered a classical science, the realm of chemistry and Newtonian mechanics. The warm, wet, and messy environment of a living cell seemed the absolute worst place for delicate quantum effects like superposition and entanglement to survive. Decoherence should smash them apart in an instant, yet a revolutionary field called quantum biology is uncovering something astonishing. Life may not just exist in the quantum world. It may have learned to use it. The first and most compelling evidence comes from the very process that powers our planet, photosynthesis. Inside the leaves of plants, algae, and some bacteria are light-harvesting complexes, intricate molecular antennae that capture sunlight. The energy from a captured photon needs to be transported to a reaction center where it can be converted into chemical fuel. Classically, scientists thought this transport was a random, haphazard walk, like a drunkard stumbling through a crowd. This should be inefficient, with much of the precious energy lost as heat. Yet photosynthesis is staggeringly efficient, often approaching 100%. How experiments using ultra-fast lasers have revealed a quantum secret. The energy does not take a single path. It explores all possible pathways at once. The exciton, the packet of energy from the photon, exists in a short-lived state of quantum coherence, a superposition spreading through the molecular network like a wave exploring multiple routes simultaneously. It essentially performs a quantum computation to find the most efficient path to its destination before decoherence sets in. Life has been using quantum search algorithms for billions of years. This quantum advantage is not confined to plants. Consider the mysterious ability of migratory birds to navigate using Earth's faint magnetic field. The leading hypothesis involves a quantum process in their eyes. It is thought that light hits a protein called cryptochrome, triggering the creation of a pair of molecules with unpaired electrons, known as a radical pair. These two electrons are quantum entangled, their spins correlated. Earth's magnetic field, incredibly weak compared to a fridge magnet, can influence the spin states of this entangled pair. Different spin states lead to different chemical outcomes in the protein, effectively creating a chemical compass that tells the bird which way is north. The bird may literally see the magnetic field as a visual pattern, a quantum sense woven into its perception. Even our own sense of smell might have a quantum dimension. The standard lock and key model suggests odor molecules fit into specific receptors based solely on their shape. But scientists have found molecules with identical shapes that smell completely different, and molecules with different shapes that smell the same. An alternative theory proposes that what we smell is not the shape, but the vibrational frequency of the bonds within the molecule. The mechanism could involve quantum tunneling, where electrons in the receptor tunnel across only if the vibration of the odor molecule provides the right quantum of energy. This inelastic electron tunneling would act as a spectral analyzer, reading the molecular music. If true, every time you smell a rose or fresh coffee, you are performing a quantum measurement. These discoveries are transforming our understanding of life. They suggest evolution is not just a classical tinkerer, but a quantum engineer. In the noisy, chaotic environment of a cell, life has found ways to protect and exploit quantum phenomena long enough to gain a functional advantage. It uses coherence for perfect efficiency, entanglement for navigation, and tunneling for perception. This implies that the quantum world is not a separate, alien domain. It is the substrate from which life emerged and the toolkit it uses to thrive. the boundary between the quantum and the classical, between physics and biology, begins to blur. We are not just observers of the quantum realm. We are, in a very real sense, its most sophisticated creations. The idea that life itself might be a quantum technology rests on a reality so strange that even its discoverers refuse to believe it. The phenomenon of entanglement, which birds may use to navigate and plants to harvest light, was once considered a fatal flaw in quantum theory, a ghost in the machine that had to be explained away. This battle over the soul of physics was crystallized in a devastating thought experiment conceived by Albert Einstein and his colleagues Boris Podolsky and Nathan Rosen in 1935. Their goal was not to explore entanglement, but to destroy it, to prove that quantum mechanics was an incomplete description of reality. They began with a principle they held sacred: local realism. Locality means that no influence can travel faster than light. Realism means that particles have definite properties like position and spin, even when we are not looking at them. To them, the universe was a collection of separate objects with pre-existing attributes, like distant stars whose light had already been emitted long before we see it. Quantum entanglement, with its spooky instantaneous connection, violated both. So Einstein, Podolsky, and Rosen devised a clever logical trap, now called the EPR paradox. Imagine you create two entangled particles, like two electrons with linked spins, and fly them to opposite sides of the galaxy. You do not measure them. According to quantum mechanics, each particle's spin is indefinite, a superposition of up and down. Now, an experimenter on one side chooses to measure her particle and finds its spin is up. Instantly, she knows with certainty that the particle on the other side of the galaxy must be down. The paradox, as Einstein saw it, was this: how could the second particle know to be down unless that information traveled faster than light? And if it was always destined to be down, then it must have had that definite property all along, meaning quantum mechanics was incomplete for not describing it. He argued there must be hidden variables, unseen instructions the particles carried from birth that predetermined their correlated outcomes. There was no spooky action, just a pre-arranged harmony. For 3 decades, this remained a philosophical debate, a clash of worldviews with no way to test who was right. Then, in the 1960s, a brilliant physicist named John Bell changed everything. He asked a profound question: could the correlations between entangled particles be explained by any local hidden variable theory, any pre-arranged plan that respected the speed of light? He derived a mathematical inequality now known as Bell's theorem. It stated that if local realism were true, the statistical results of certain measurements on entangled pairs would always stay within a specific, limited range. But if quantum mechanics was correct and the particles were truly connected non-locally, the results would violate that limit, bursting through Bell's inequality. He had turned a metaphysical argument into an experimental recipe. The race was on to build the test. In the early 1980s, a French team led by Alain Aspect performed a series of landmark experiments. They created pairs of entangled photons and sent them in opposite directions to detectors that could rapidly and randomly switch their measurement settings while the photons were in flight. This closed a critical loophole, ensuring the measurement choice on one side could not possibly signal to the other particle what to be. The results were unambiguous. Quantum correlations violated Bell's inequality by a wide margin. The universe had chosen. There were no local hidden variables. No pre-arranged plan could explain the perfect instantaneous correlation. Spooky action at a distance was not a flaw, it was a feature of reality. Subsequent experiments over decades, closing other loopholes with even greater precision, have only reinforced this stunning conclusion. The EPR paradox, intended to bury quantum weirdness, instead became its most triumphant validation. Einstein's cherished local realism, the common-sense view of a universe made of separate, definite things, was experimentally falsified. This forced a profound and permanent rethink. Entanglement was not a mathematical artifact. It was as real as gravity, a non-local thread stitching the universe together at its fundamental level. The particles were not distant actors following a script. They were parts of a single, inseparable whole, a quantum entity that laughs at the concept of space. The implications ripple out to everything we have discussed, from the holographic principle to the nature of time itself. If the universe is not locally real, then what is it? The defeat of local realism opened a door to a technology that once seemed pure fantasy. Quantum teleportation is real, but it bears little resemblance to the transporter beams of science fiction. This is not about dematerializing a person and rebuilding them across space. It is something both more subtle and more profound, the flawless transfer of a quantum state from one particle to another, a ghostly transmission made possible by spooky action itself. The protocol is a beautiful dance of entanglement and classical information, a three-step process that feels like a magic trick with the universe. First, you need a pair of entangled particles. Let us call them particle B and particle C. You create them together, their fates forever linked, and you physically separate them. You give particle B to your friend Alice, and you send particle C far away to your other friend Bob. Now you have a third particle, particle A, which contains the precious quantum state you want to teleport, perhaps a specific spin or polarization that encodes a piece of information. You do not know what this state is, and crucially, you cannot simply measure it to find out, because a measurement would collapse it and destroy its delicate quantum nature. Here is where the magic begins. Alice takes a particle B and performs a special joint measurement on it together with the mystery particle A. This measurement entangles A and B, but in doing so, it completely scrambles the quantum state of particle A. It is gone, however, because B was already entangled with C. This act instantly affects particle C, now held by Bob far away. But Bob's particle is not yet in the desired state. It is in a jumbled state related to the original. Alice now must send Bob the results of her measurement using ordinary, classical communication, a phone call or an email limited by the speed of light. This is the second critical step. Only when Bob receives this classical information can he perform the final step, applying a specific correction like a quantum password to his particle C. Once he does, particle C emerges in the exact original quantum state that particle A once held. The original particle A is left behind, its state obliterated. The information has been teleported, not copied. The quantum no-cloning theorem ensures the original is always destroyed, preserving the sacred uniqueness of quantum information. This has been successfully demonstrated in labs across the world, teleporting states between photons across cities and even from the ground to a satellite in orbit. The promise of this is the backbone of a future quantum internet. Imagine a network where quantum computers are linked not by slow, classical cables, but by teleportation channels. They could share processing power, creating a distributed supercomputer of unimaginable capability. More immediately, it enables quantum repeaters, devices that can extend the range of perfectly secure quantum cryptographic keys over global distances, fighting the signal loss that plagues fiber optic cables. This is not a distant dream, it is the engineering roadmap being drawn today, turning the spookiest action in physics into the most secure communication system ever conceived. But teleportation relies on knowing a measurement was made. What if you could erase that knowledge even after the fact? The quantum eraser experiment is a delayed choice puzzle that suggests reality might not just be spooky, but profoundly indecisive about its own history. It builds upon the classic double slit, but adds a twist that feels like rewriting the past. Recall that when you detect which slit a particle goes through, the interference pattern vanishes. The particle acts like a single object. When you do not detect the path, you get an interference pattern, the signature of a wave. The quantum eraser asks, what if you could make that choice after the particle has already hit the final screen? The setup involves adding a subtle layer to the double slit. Scientists use a special crystal that can split a single photon into two entangled photons, often called the signal photon and the idler photon. The signal photon is sent toward the double slit apparatus. Its entangled twin, the idler photon, is sent on a different path toward a set of detectors that can be configured in different ways. Now here is the crucial sequence. The signal photon passes through the slits and hits the main screen where its arrival point is recorded. This happens first. Only after it has been detected do the experimenters decide what to do with its entangled partner, the idler photon. In one configuration, they can use the idler photon to determine which slit the signal photon came from. When they do this, looking back at the data from the signal photons that have already been detected, they find no interference pattern. The signal photons behaved like particles. In another configuration, they use a different optical setup to erase the which path information carried by the idler photon. They make it fundamentally impossible to tell which slit the signal photon used. When they perform this quantum erasure and then look at the same set of already recorded signal photon hits, an interference pattern magically reappears in the data. It is as if the later choice of whether to erase or keep the path information retroactively decided whether the signal photon, which had already finished its journey, traveled as a particle or a wave. The past seems changeable, contingent on a future decision. This is not time travel in the classic sense. The individual detection events on the screen do not move. But the pattern they collectively form, the story they tell about what kind of object the photon was, depends on an event that happens later. How can we make sense of this? One interpretation leans into the block universe idea suggested by timeless equations. In this view, all of time, past, present, and future, exists as a single, unchanging four-dimensional structure. Our conscious experience of moving through it is an illusion. From this God's eye perspective, the erasure choice is not after the detection. Both events are just fixed points in the block. The universe simply ensures consistency across its entire timeline. The pattern on the screen and the configuration of the eraser are correlated parts of a single, coherent whole. There is no rewriting of history, only a revelation of a history that was always interconnected. A more radical interpretation is retrocausality, the idea that influences can travel backward in time. Perhaps the future choice to erase information sends a subtle signal backward, instructing the photon to have taken both paths. This violates our everyday intuition but is not strictly forbidden by the mathematics of quantum mechanics. It suggests causality might be a two-way street at the quantum level. Most physicists favor a less mystical explanation rooted in non-locality and entanglement. The signal and idler photons are one quantum system. The act of erasing or not erasing the idler's path information changes the entire context for how we interpret the data from the signal. It does not change the individual detection events, but it changes which subsets of those events are correlated and can reveal an interference pattern. The interference was always potentially there in the data, hidden in the noise, waiting for the right context to be unveiled. The quantum eraser does not let us send messages to the past, but it does something perhaps more profound. It demonstrates that in the quantum realm, the very concepts of before and after, of cause and effect, become blurred. An event's meaning, its place in a causal story, is not fixed until the entire experimental context, including future choices, is accounted for. The universe seems less like a chain of dominoes falling in sequence, and more like a finished painting where the meaning of a single brushstroke only becomes clear when you finally step back and see the whole picture. This indecisive nature of quantum history points toward a deeper, hidden symmetry in the universe's design. One of the most elegant and ambitious ideas in modern physics proposes that for every particle we know, there exists a hidden twin, a superpartner. This is the theory of supersymmetry, or SUSY, a beautiful mathematical framework that could solve several of our greatest cosmic puzzles in one stroke. The core idea is stunningly simple. It suggests a fundamental symmetry between the two great families of particles, the fermions and the bosons. Fermions, like electrons and quarks, are the building blocks of matter. Bosons, like photons and gluons, are the force carriers that glue matter together. Supersymmetry proposes that every fermion has a bosonic superpartner, and every boson has a fermionic superpartner. The electron would have a partner called the selectron. The photon would have the photino. The familiar zoo of particles would double in size, revealing a hidden mirror universe of shadow particles. Why would nature require such extravagance? The answer lies in solving one of physics' most annoying fine-tuning problems, the hierarchy problem. This is the question of why the Higgs boson, the particle that gives others mass, is so incredibly light compared to the immense energy scale of gravity. In the quantum vacuum, virtual particles constantly pop in and out, and their interactions should drive the Higgs mass up to the colossal Planck scale, making it 100 million billion times heavier than it is. For our universe of atoms and chemistry to exist, an absurdly precise cancellation of these quantum effects must occur, a coincidence so unlikely it feels like the universe is balanced on a knife's edge. Supersymmetry provides a graceful escape. For every known particle contributing to the Higgs mass, its superpartner contributes an equal but opposite amount. They are perfect dance partners, their quantum effects cancelling each other out naturally, stabilizing the Higgs mass without any miraculous fine-tuning. The symmetry protects the fragility of our world. Beyond this, supersymmetry offers a perfect candidate for the universe's missing mass. The lightest superpartner, often neutral and stable, would not interact with light or ordinary matter very much, just drifting through the cosmos unseen. It fits the description of dark matter perfectly, a shadow particle born from pure mathematical symmetry that could make up over a quarter of everything that exists. Furthermore, SUSY is not just an add-on. It is a required ingredient for string theory to work, providing the mathematical glue that allows the theory's vibrating strings to include all the forces and matter we see. It represents a dream of unification where all forces become one at incredibly high energies. Yet for all its beauty and promise, supersymmetry faces a stark experimental reality. The Large Hadron Collider, the most powerful particle smasher ever built, was designed in part to discover these superpartners. Physicists hoped they would appear at energy scales just above those of the known particles. But after years of smashing protons together at unprecedented energies and sifting through the debris, no clear signal of a selectron, photino, or any superpartner has emerged. The elegant simplicity of the original SUSY models has been forced to retreat into more complex and higher energy territories. This does not kill the theory, but it places it in a precarious and fascinating position. It may be that superpartners are simply much heavier than we hoped, waiting for a more powerful collider to reveal them. Or perhaps they hide in ways we have not yet learned to detect, decaying into unusual signatures we are only beginning to search for. The absence of evidence is not evidence of absence, but it is a profound challenge. Supersymmetry remains a towering achievement of theoretical physics, a vision of such compelling elegance that many physicists feel it must be true in some form. It represents the human mind's drive to find order and symmetry in the chaos of quantum data, to believe that behind the apparent randomness lies a hidden, beautiful structure. The search continues, a testament to our hope that the universe is not just strange, but also profoundly simple and symmetrical at its heart. The absence of superpartners in our universe would be no mystery at all if they simply reside in another. This is the staggering proposition of the multiverse, an idea that quantum mechanics itself seems to demand. Our journey through quantum mysteries has repeatedly shown reality refusing to choose a single path. The many worlds interpretation takes this refusal to its ultimate conclusion. It states that every quantum event with more than one possible outcome does not resolve into one. Instead, the universe itself splits, giving birth to parallel realities where every possibility is realized. When a radioactive atom decays, in one branch it does, and in another it does not. When you decide to turn left instead of right, a new universe branches where your other self turns right. Every flutter of every electron, every random quantum fluctuation, becomes a fork in the road of existence, spawning an ever-expanding, infinite tree of alternate histories. In this view, Schrödinger's cat is never in a box both alive and dead. There is one universe with a living cat and a relieved scientist, and another, equally real universe with a dead cat and a grieving one. The wave function never collapses, it merely branches, and we find ourselves riding one thread of that infinite tapestry, unaware of the others. This is a multiverse born purely from the mathematics of quantum mechanics, a proliferation of worlds emerging from every microscopic choice. Yet there is another, equally profound vision of the multiverse that comes not from quantum branching, but from cosmic inflation. This theory describes the Big Bang as a moment of exponential, faster-than-light expansion of space itself. Some versions suggest this inflationary process is eternal, never truly stopping everywhere at once. In this eternal inflation, pockets of space can stop inflating and settle into stable universes like our own, while the space between them continues to expand furiously. Each of these bubbles would have its own random set of physical constants, its own laws of physics. Some might be sterile voids, others might be brimming with life under different rules. In this cosmic foam of bubble universes, we simply inhabit one bubble where the constants allowed stars and planets to form. This is a multiverse of cosmology, a vast collection of disconnected realms with potentially different fundamental laws. While distinct in origin, the quantum and cosmological multiverses share a radical philosophical implication. They suggest our universe is not unique. Everything that can happen does happen somewhere in the vast ensemble of realities. This idea challenges our deepest notions of self and significance. Are you special? In a multiverse, there are countless versions of you, each having made different choices, living different lives. Your greatest triumphs and deepest regrets are both realized in full elsewhere. This can feel liberating or profoundly lonely, but is it science or just metaphysics? The central criticism is testability. If these other universes are permanently disconnected from our own, can we ever gather evidence? Proponents point to subtle clues. The mysterious low value of dark energy might be explained if we live in a bubble universe where inflation randomly settled on a life-permitting number. The pattern of the cosmic microwave background, the afterglow of the Big Bang, might contain imprints of collisions with other bubble universes in the distant past. For the quantum multiverse, some suggest that the faint, unexplained noise in certain superconducting circuits could be the whisper of other branches interfering with our own. While definitive proof remains elusive, the multiverse is not a casual speculation. It emerges as a natural, even inevitable, consequence of taking our best theories of the quantum and the cosmic to their logical extremes. It forces us to confront a humbling possibility. The complete story of reality may be a story we can never fully read, because most of its chapters are written in universes forever beyond our reach. If the multiverse contains every possible version of you, which one is the real you? This question leads us to the most intimate and contentious frontier of all, the mystery of quantum consciousness. The proposal is as bold as it is divisive. What if our awareness, the very essence of subjective experience, is not a classical byproduct of neural computation, but a direct manifestation of quantum processes happening inside our brains? The most famous model for this idea comes from the collaboration of physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. Their theory, called orchestrated objective reduction, suggests that consciousness arises from quantum computations within structures inside our neurons called microtubules. Microtubules are part of the cell's skeleton, tiny cylindrical structures that help maintain shape and transport materials. Penrose and Hamroff propose they are far more than cellular scaffolding. They theorize that the interiors of these microtubules are perfectly suited to protect delicate quantum states from the noisy warmth of the brain. Within them, electrons could become entangled and exist in superpositions, performing a kind of quantum processing. Penrose further argues that this quantum computation is linked to a fundamental incompleteness in our understanding of reality, specifically the mystery of wave function collapse. He believes consciousness is the process by which quantum superpositions in the brain reach a threshold and collapse, with each collapse giving rise to a discrete moment of awareness, a flicker of conscious thought. In this view, your mind is not a classical computer. It is a quantum orchestra, with each reduction of a quantum state producing a note in the symphony of your experience. This would elegantly tie the hardest problem in neuroscience, explaining why we have subjective feelings at all, to the hardest problem in physics, the measurement problem. The appeal is undeniable. It places consciousness at the very heart of physical reality, not as an accidental epiphenomenon, but as an active participant in the quantum world. Yet this theory has faced a tidal wave of criticism from the mainstream scientific community. Neuroscientists and physicists alike point to a formidable obstacle: decoherence. The brain is a wet, warm, and chaotic place. It is about 37 degrees Celsius, awash in biochemical soup and electrical noise. Maintaining the delicate, coherent quantum states necessary for such processing for even a fraction of a second under these conditions is, according to most experts, physically impossible. Any quantum superposition in a microtubule would be smashed apart by its environment almost instantly, far too quickly to influence any neural process that could be linked to conscious thought. Critics argue that classical explanations of neural network interactions are sufficient to explain cognition and behavior, and that invoking quantum mechanics is an unnecessary complication, a solution in search of a problem. They see it as a modern form of vitalism, attempting to explain a mysterious phenomenon with another, equally mysterious one. The debate is heated precisely because the stakes are so high. If quantum processes are involved in consciousness, it would revolutionize our understanding of both the mind and the universe. It would mean that the observer effect is not just a laboratory curiosity, but a biological fact. Our inner world of thoughts and feelings would be a direct window into the quantum foundation of reality. If not, then consciousness remains an emergent property of complex classical computation, a ghost in the classical machine, leaving the hard problems stubbornly unsolved. For now, the theory of quantum consciousness remains on the fringe, a captivating but unproven bridge between two great unknowns. It stands as a testament to our deepest desire, to find our own minds reflected in the fabric of the cosmos, to discover that we are not just observers of the quantum mystery, but its living, breathing expression. The debate over consciousness reveals a deeper truth about our place in time. We feel it flowing in one direction only, an arrow pointing from a fixed past toward an open future. But why, at the quantum level, the laws of physics are almost perfectly time-symmetric? They work just as well running backward as forward, yet our lived experience is a one-way street. We remember yesterday, we anticipate tomorrow, and we cannot unbreak an egg. This is the thermodynamic arrow of time, defined by the relentless increase of entropy or disorder. And its origin may be a quantum story written in the act of measurement itself. Every time a quantum superposition collapses into a definite state, it creates information. That photon hitting a detector leaves a mark, an irreversible record etched into the universe. This process is fundamentally one-way. You cannot take that recorded dot of light and unscramble it back into a superposition of possibilities. Each quantum measurement is a tiny, irreversible step that increases the total information, and thus the entropy of the cosmos. Our memories are vast collections of such quantum records, stable imprints in our neural architecture that tell a story of cause and effect. We remember the past because it is a landscape of fixed quantum outcomes, a trail of breadcrumbs that cannot be uneaten. The future, by contrast, remains a haze of quantum potential, a superposition of possibilities not yet collapsed into history. So the flow of time we feel may be the accumulated sensation of trillions of quantum measurements happening every instant, each one nailing down a bit of reality and pushing the universal clock forward one tick. This raises a monumental question. If quantum processes fuel the arrow of time, what set it in motion at the beginning of everything? Why did the universe start in a state of incredibly low entropy, a pristine order that has been unraveling ever since? The Big Bang appears as a singular point of near-perfect symmetry and minimal disorder. From that starting line, the great unwinding began, allowing for the formation of galaxies, stars, planets, and life. One radical possibility is that this initial low entropy state itself has a quantum origin. Perhaps the universe did not begin as a single, definite point, but as a quantum fluctuation, a random emergence from a prior state of nothingness or a deeper quantum field. In such a scenario, the act of its birth, the transition from quantum possibility to classical reality, was the first and ultimate measurement. That primordial collapse from a superposition of possible universes into our specific, expanding cosmos established the first irreversible record and pointed the arrow of time in a definite direction. From that moment, every subsequent quantum event has added to the stack of cosmic memory, weaving the irreversible tapestry of history. In this view, the flow of time is not an independent force. It is a cosmic echo of that first quantum choice, a phenomenon that emerges from the universe gradually remembering what it has become, one collapsed possibility at a time. This irreversible flow of time finds its most stable expression in the strange, knotted states of matter that could form the unshakable hardware of a quantum future. Beyond the familiar solids, liquids, and gases, and even beyond superconductors, lies a realm where the shape of an object's quantum wave function matters more than the material it is made from. These are topological quantum states, and they are rewriting the textbook on what matter can be. The most accessible example is the topological insulator. Picture a three-dimensional crystal that behaves like a perfect insulator in its interior, blocking the flow of electricity completely. Yet on its very surface, it becomes a perfect conductor, allowing electrons to race along with almost no resistance. It is as if you had a block of rubber that is utterly dry inside, but its outer skin is coated with a perfect layer of frictionless ice. This bizarre split personality is not an accident of chemistry or purity. It is enforced by the global shape, the topology, of the material's electronic structure. In mathematics, topology is the study of properties that remain unchanged under continuous deformation. A coffee mug and a donut are topologically equivalent because one can be smoothly morphed into the other without cutting or gluing. They both have one whole. For a topological insulator, there is a similar invariant, a quantum number that cannot change unless the system undergoes a radical phase transition. This topological protection is the magic. Ordinary conductors are plagued by defects, impurities, and vibrations that scatter electrons, creating heat and resistance. But on the surface of a topological insulator, the conducting states are so intimately tied to the material's bulk topology that local imperfections cannot destroy them. An electron flowing along that surface simply goes around any defect or impurity, its path dictated by the unchangeable topological rule. It is robust by design, a dream property for any electronic device. But the real prize lies in what happens when you combine topology with two-dimensional materials. Here, we encounter a particle that is neither a boson nor a fermion, a creature that can only exist in a flatland universe. They are called enyons. You will recall that in our three-dimensional world, particles fall into two fundamental families: Bosons, like photons, are social. They can pile on top of each other. Fermions, like electrons, are solitary, obeying the Pauli exclusion principle that keeps them apart. This distinction comes from what happens when you swap two identical particles. Swap two bosons and the quantum wave function stays the same. Swap two fermions and it picks up a phase of -1, a flip in the quantum sign. In 2 dimensions, however, the mathematics allows for a breathtaking spectrum of possibilities. Swap two identical anyons and their collective wave function can change by any phase, not just +1 or -1. They can remember the intricate braiding history of how they have been moved around one another. This makes them non-abelian anyons, a name that signifies their quantum states do not commute. The order of operations matters profoundly. Why is this more than a mathematical curiosity? Because this braiding memory is theoretically immune to decoherence. In a topological quantum computer, information would not be stored in fragile individual qubits like trapped ions or superconducting loops. Instead, it would be encoded in the collective topological state of many anyons. To perform a computation, you would physically braid these anyons around each other in space. The specific braid pattern would execute the quantum logic gate. The final result, the answer, would be read out by observing the collective state. The revolutionary advantage is that the information is not stored locally. It is delocalized across the entire system, woven into its global topology. A local perturbation, a stray bit of heat, or a microscopic defect cannot peek at or corrupt this information because it is not stored in any one place. It is like writing a secret message not with ink on paper, but in the specific knotting of a network of strings. To read it, you need to see the whole pattern. This makes topological quantum computing the holy grail, a potentially fault-tolerant path to scalable quantum machines. While still largely in the theoretical and early experimental stage, the hunt for these exotic particles is fierce. Scientists create artificial flatlands in semiconductor sandwiches, chilling them to near absolute zero and subjecting them to immense magnetic fields, searching for the telltale signatures of anyonic behavior. Each tentative success is a step toward a computer built not on silicon, but on the timeless knots of quantum geometry. Even the most delicate quantum measurement is a violent act, a sudden forcing of possibility into fact. But what if we could just peek? This is the promise of weak measurement, a technique so subtle it allows scientists to glimpse the quantum world without waking it from its dream of possibilities. Instead of a hammer blow that shatters a superposition, a weak measurement is a feather light touch, a gentle probe that extracts only a tiny amount of information. The system is barely disturbed, its wave function not fully collapsed, and over thousands of repetitions, a ghostly average path begins to emerge. It is like trying to track a shy animal at night, not by shining a bright spotlight that would scare it away, but by using many faint flashes of dim light, each one revealing only a blurry hint of its position. By compiling these hints, you can map out its most likely trail. When this technique was applied to the iconic double-slit experiment, the results were nothing short of astonishing. For decades, the standard story was clear. A particle does not have a trajectory until you measure it. It is a wave that goes through both slits, and only upon detection does it materialize at a specific point. Weak measurement challenged this narrative head-on. By making gentle, non-disruptive measurements of photon positions as they traveled from the slits to the screen, researchers were able to reconstruct average paths. These paths were not the straight lines you might expect from a classical particle. They were intricate, weaving patterns that looked exactly like the trajectories predicted by a long-neglected interpretation of quantum mechanics called de Broglie-Bohm theory or pilot wave theory. In this view, particles are real and have definite positions at all times, but they are guided by a mysterious pilot wave that emanates from the entire experimental setup. The wave goes through both slits and interferes with itself, creating a landscape of high and low probability. The particle, like a surfer, is then carried along a specific path dictated by this wave, inevitably landing where the wave's intensity is highest, creating the interference pattern. The weak measurement results seem to show these surfers' paths in stunning detail, curved rivers of probability flowing from the slits to the bright bands on the screen. This does not prove pilot wave theory is correct, but it does open a profound window. It suggests that there may be a hidden layer of reality between the definite particle and the ethereal wave, a realm of average behaviors and subtle influences that standard quantum mechanics sweeps under the rug. Weak measurement allows us to ask questions we were told were meaningless, like what path did the particle take, and get a statistical answer that paints a startlingly concrete picture. It reveals a quantum world not of pure randomness, but of guided chaos, where particles trace out ghostly trajectories that only become visible when we learn to look without staring. This technique is now a powerful tool for probing other quantum mysteries, from the flow of energy in photosynthesis to the strange topology of exotic materials. It teaches us that sometimes to see the truth most clearly, you must learn to squint. This staggering mismatch of 120 orders of magnitude is not a minor error. It is the most severe failure of prediction in the history of science. To grasp the scale of this failure, consider the difference between the size of a single proton and the size of the entire observable universe. That immense gap is only about 40 orders of magnitude. Our quantum vacuum prediction is off by a factor that is a trillion times larger than that already unimaginable difference. It means our theoretical estimate for the energy of empty space is catastrophically, impossibly wrong. If it were correct, the repulsive force would have been so strong that the universe would have blown itself apart in the first fraction of a second, shredding every atom before it could even form. No stars, no planets, no life would ever have been possible. Yet here we are in a cosmos that is expanding, but at a remarkably gentle, almost lazy pace. This is the cosmological constant problem, and it screams that something fundamental is missing from our picture of reality. Why is the observed value of dark energy so infinitesimally small, yet not perfectly zero? This delicate balance is the razor's edge upon which all of existence teeters. It feels less like a natural law and more like a cosmic coincidence of impossible precision. To solve it, physicists have been forced to consider some of the most radical ideas in cosmology. One controversial but compelling explanation leans into the multiverse concept we explored earlier. It is called the anthropic principle. In a vast landscape of bubble universes, each with randomly determined physical constants, the value of the vacuum energy would vary wildly. In almost all of those universes, the value would be enormous, leading to instant dispersal or immediate collapse. Only in the exceedingly rare bubbles where the value fell within a vanishingly narrow window could galaxies, stars, and life like us ever arise. We, of course, find ourselves in one of those rare, life-permitting bubbles. In this view, the cosmological constant is not fine-tuned for us. We are the accidental product of its rare, habitable setting. The problem is not solved, but explained away by our own existence. This idea is deeply unsatisfying to many scientists who seek a dynamical, physical reason for the number we see. This search has led to the proposal of quintessence. Unlike a static cosmological constant, quintessence is a dynamic field, a kind of fifth fundamental force that permeates space and changes slowly over cosmic time. Imagine it not as a fixed energy of the vacuum, but as a kind of cosmic weather, a gentle pressure that has varied over the 14 billion-year history of the universe. In some models, this field was nearly dormant during the early epochs, allowing galaxies to form, and only recently became dominant, beginning the accelerated expansion we see today. It could even decay further in the distant future. The appeal of quintessence is that it replaces a mysterious, fixed number with a changing entity governed by equations we might one day discover. Yet despite decades of searching, no definitive evidence for quintessence has been found. The observed dark energy behaves so far exactly like a simple, unchanging constant. This leaves us with a haunting possibility. Perhaps the solution lies not in adding new fields, but in a profound misunderstanding of gravity itself. Maybe Einstein's theory of general relativity, while spectacularly successful, breaks down on the scale of the entire cosmos. The cosmological constant problem may be the universe's way of telling us that our theory of gravity is an approximation, a shadow of a deeper truth that seamlessly blends the quantum and the cosmic. The energy of nothingness remains the loudest silence in physics, a whisper from the vacuum that we have not yet learned to interpret. This ghostly selection of reality leads to a startling new principle: quantum Darwinism. It is a theory that proposes our solid, objective world does not emerge from a single, mysterious collapse, but through a process of information survival, a kind of natural selection for facts. The central idea is that when a quantum system interacts with its environment, it does not just decohere. Specific information about the system gets copied over and over again into the surrounding environment. Think of a stone dropped into a pond. The splash is the quantum event, but the reality of that splash is not defined by the initial disturbance. It is defined by the countless overlapping ripples that spread outward, each one carrying a copy of the information that a stone hit the water. Any observer who comes along can learn about the stone by intercepting just a few of those ripples. They do not need to see the original splash. In quantum Darwinism, the environment acts as that pond. When you look at a table, you are not directly interacting with the quantum wave functions of its trillions of atoms. You are intercepting photons of light that have bounced off it. Each of those photons has become entangled with the table, picking up information about its position, color, and shape. That same information is imprinted on trillions of other photons, air molecules, and dust particles. The information about the table's location and existence is redundantly copied into the environment. This redundancy is key. It is what makes a fact objective. For a property to be considered objectively real, many observers must be able to measure it independently and agree on the result. Quantum Darwinism explains how this happens. The quantum system, through relentless interaction, broadcasts specific information about certain preferred states into the environment. Other states, which do not get copied and amplified in this way, simply fade away, becoming inaccessible. The surviving information is what we all agree upon as reality. It is the pointer states, the classical properties like position and momentum, that win the Darwinian competition. Why do these particular properties win? Because they are robust. They are the states that can withstand interaction with the environment without being completely scrambled. A table's position is a stable fact because photons bouncing off it reliably carry that information away. More fragile quantum superpositions of position cannot survive this broadcasting process. They decohere before their information can be widely copied. So the world you see is not an arbitrary selection from the quantum soup. It is the subset of quantum possibilities that are fit enough to reproduce their information, that can imprint themselves on the world around them. Your consciousness is not doing the selecting. You are simply a gatherer of that widely available, redundantly stored data. This framework elegantly bridges the quantum and classical realms without invoking mysterious collapses or conscious observers. Objective reality emerges not from a single act of observation, but from the proliferation of information, from the universe's relentless habit of taking notes. It suggests that what we call the present moment is a consensus, a story being told by the environment itself, a narrative so widely published that we all cannot help but read the same page. Even the vacuum's silence depends on how you move through it. The unrun effect is a prediction so strange it redefines the concept of nothingness. According to this idea, empty space is not the same for everyone. Imagine two astronauts floating in what seems to be a perfect cold vacuum, utterly devoid of particles. One astronaut continues to drift, inert and weightless. The other fires a rocket pack, accelerating steadily through the void. For the drifting astronaut, nothing changes. The vacuum remains empty, a silent, sterile freeze. But for the accelerating astronaut, something miraculous and bizarre occurs. Their instruments would detect a faint warmth, a gentle bath of heat radiation. To them, the vacuum is no longer empty. It is filled with a sea of real, detectable particles, a thermal glow born from pure motion. This is UNRRA radiation, and it tells us that particles themselves are not absolute fixtures of reality. They are relative, emerging from the interaction between an observer's state of motion and the underlying quantum fields. The mathematics reveals that an accelerating observer's path through space-time mixes positive and negative frequency modes of the quantum field in a way that appears as a thermal spectrum, a real heat signature. The faster the acceleration, the hotter this perceived bath of particles becomes. This is not a quirk of faulty instruments. It is a fundamental statement about what exists. What one observer swears is empty space, another swears is a particle-filled furnace. Both are correct within their own frame of reference. This effect is not just a theoretical curiosity. It is the direct, conceptual cousin of Hawking radiation from black holes. The immense gravitational pull at the event horizon is, from the perspective of quantum field theory, a form of relentless acceleration. A particle falling in experiences tidal forces that stretch it apart, an acceleration so extreme it rips virtual pairs from the quantum foam, allowing one to escape as real radiation. The mathematics describing the glow of a black hole and the glow felt by an accelerating astronaut are deeply connected, two faces of the same quantum truth. The UNRRA effect blurs the line between matter and motion to the point of dissolution. It suggests that what we call a particle is not a fundamental building block, but an excitation, a note played on the quantum field that only becomes audible to an observer moving in the right way. Your entire perception of the material world, the solidity of objects around you, could be a story told by your particular journey through the cosmos. If you were accelerating at a truly monstrous rate, the void around you would blaze with particle creation, a universe of matter conjured from nothing but your own motion. This forces a humbling conclusion. There is no God's eye view of the vacuum, no privileged frame that defines true emptiness. Existence itself is a participatory phenomenon, a dance between the field and the frame, where even the act of moving can summon worlds from the dark. The UNRRA effect reveals that reality is a story told by motion, but some journeys lead to a place where all stories end. At the very heart of a black hole, according to Einstein's equations, lies a singularity. This is not a place you can visit. It is a mathematical point of infinite density where the curvature of space-time becomes infinite and the known laws of physics cease to have any meaning. General relativity, our magnificent theory of gravity, predicts its own downfall here. It is a screaming signal, a cosmic error message written in the fabric of reality itself, telling us we need a deeper theory. The singularity is where the smooth geometry of space-time meets the granular quantum world, and the collision is catastrophic. It represents the ultimate breakdown of our classical picture, a place where matter is crushed out of existence and time itself is thought to stop. For decades, this was seen as the final tomb for anything that fell in, a one-way trip to a mathematical oblivion, but quantum mechanics abhors infinities. In nature, true infinities are almost always a sign that a theory has been pushed beyond its limits, that we are missing a crucial piece of the puzzle. The quest to resolve the black hole singularity is the front line in the battle for a theory of quantum gravity. The leading idea is that quantum effects must step in before matter reaches that impossible point of zero volume. Just as quantum mechanics prevents an electron from crashing into an atom's nucleus by giving it a fuzzy cloud of probability, it may prevent total collapse by imposing a fundamental granularity to space itself. In the theory of loop quantum gravity, space is not smooth and continuous. It is woven from tiny, finite loops, a fabric with a smallest possible weave. This means there is a smallest possible unit of volume, a quantum of space. When matter collapses under its own gravity, it cannot squeeze into a point of zero size. Instead, it compresses down to this smallest possible volume, a sphere about 1 trillion times smaller than an atom at the Planck scale. At this incredible density, the quantum pressure from the granularity of space becomes unimaginably strong, like a cosmic spring compressed to its absolute limit. The result is not an infinite singularity, but a rebound. The collapse stops and reverses. Matter experiences a quantum bounce. This hypothetical object at the core is sometimes called a Planck star. It is not a star in the traditional sense, shining with nuclear fusion. It is a knot of space-time and matter under such extreme quantum tension that its eventual expansion could be incredibly slow from our outside perspective, taking billions of years, while from inside the bounce happens in an instant. This idea transforms a black hole from a cosmic dead end into a potential gateway. The interior might not be a one-way street to a singularity, but a region of highly warped space leading to a bouncing core. Some speculative theories even suggest that this bounce could eventually lead to the birth of a new universe, a baby cosmos budding off from our own with its own spacetime and laws. While this remains highly theoretical, the core insight is profound. The black hole singularity is not an end but a signpost. It points to a new physics where quantum geometry takes over, where the very concepts of inside and outside are rewritten, and where even the most destructive forces in the cosmos may contain the seed of a new beginning. The singularity is not an end but a question, and the questions it asks force us to confront the most basic puzzle of all. What do the equations of quantum mechanics actually mean? We have been navigating a landscape of astonishing phenomena, but the map itself is written in a language of probabilities and wave functions. The mathematics works with breathtaking precision, predicting experimental outcomes to many decimal places. Yet it offers no single story about what is happening behind the scenes. This has given rise to a constellation of interpretations, each taking the same flawless math and weaving from it a radically different narrative of reality. Choosing between them is not about right or wrong calculations, but about the kind of universe you believe you live in. The oldest and still most commonly taught is the Copenhagen interpretation. Developed by Niels Bohr and Werner Heisenberg, it takes a pragmatic, almost operational stance. It says the job of quantum mechanics is not to describe an objective reality independent of measurement. Its job is to predict the outcomes of experiments. The wave function is not a physical thing, but a mathematical tool for calculating probabilities. When a measurement occurs, the wave function collapses and a single definite result emerges. The Copenhagen interpretation draws a sharp line between the quantum system and the classical measuring apparatus. It does not dwell on what happens during collapse or what a measurement truly is. For many working physicists, this is enough. It is the recipe that builds lasers and predicts chemical bonds. But for those asking deeper questions, its silence on the nature of reality feels like a philosophical surrender. In stark opposition stands the many worlds interpretation. It refuses to accept collapse as a fundamental process. Instead, it takes the wave function with absolute seriousness as a real, evolving entity. Every time a quantum system faces a choice, like a particle being spin up or spin down, the universe does not choose. It splits. All possibilities are realized, each in a newly branched parallel world. There is no collapse, only endless branching. In this view, Schrödinger's cat is never in a box, both alive and dead. there is a universe with a live cat and another, equally real universe with a dead one. The appeal is its elegant simplicity. It removes the special, unexplained role of measurement. The cost is an almost infinite multiplicity of unseen worlds, a multiverse where every quantum possibility is someone's reality. Then there is the road less traveled, the de Broglie-Bohm or pilot wave interpretation. This theory boldly reinstates a concrete reality. It says particles are real, point-like objects that always have definite positions. But they are guided by an invisible pilot wave, the wave function itself, which permeates all of space. This wave goes through both slits, interferes with itself, and creates a landscape of high and low probability. The particle, like a surfer, is carried along a specific path dictated by that wave. This explains the double slit results without resorting to magical collapse or branching worlds. It provides a clear, deterministic picture, but at the price of non-locality, the pilot wave connects everything instantaneously, and a certain mathematical complexity that many find inelegant. Other interpretations try to modify the rules. Objective collapse theories propose that the wave function does collapse, but it is a real physical process, not something triggered by consciousness. They introduce a tiny, spontaneous collapse mechanism that becomes significant for large objects, explaining why cats are never in superpositions. These theories make testable predictions that differ from standard quantum mechanics, and experiments are seeking those subtle differences. So why does this philosophical debate matter? Because the interpretation you choose shapes your fundamental conception of what is real. Is the universe a single, ambiguous potential that crystallizes upon observation? Is it a forever branching tree of every story that could be told? Or is it a clockwork of definite particles moving along hidden, guided paths? Each interpretation answers profound questions about free will, identity, and the nature of existence in wildly different ways. Settling on one is not just an academic exercise. It determines the ultimate story we tell about our place in the cosmos, whether we are unique observers in a single unfolding drama, or merely one thread in an infinite tapestry of simultaneous lives. The equations give us the notes, but we must choose the melody. Our interpretations are maps of a territory we cannot directly see, but the border of that territory is marked by a mystery we can measure. Where exactly does the quantum world end and our classical world begin? Is it a matter of size, a switch that flips when an object becomes too big? Or is it a process, a gradual fading of quantum magic as a system interacts with its surroundings? This is the search for the quantum classical boundary, and it is a frontier being pushed in laboratories every day. For a long time, it was assumed that quantum weirdness was the exclusive domain of the very small electrons, photons, individual atoms. Surely, something as large as a molecule, let alone a cat, was simply too big to be in two places at once. The environment would destroy such delicate states almost instantly. But this was an assumption, not a law. In recent years, scientists have performed breathtaking experiments to test this limit, creating quantum superpositions with objects of ever-increasing size and complexity. They have taken molecules composed of hundreds of atoms, cooled them to near absolute zero, and sent them through versions of the double-slit experiment. These are not simple particles, they are intricate structures, little machines with moving parts, and yet they produce clear interference patterns. They act as waves, exploring multiple paths simultaneously. The current record holders are molecules like tailor-made organic compounds with thousands of atomic mass units. To put that in perspective, these are objects massive enough to be seen under powerful microscopes, yet they still obey the rules of quantum superposition under the right conditions. The experiments are a monumental feat of isolation, shielding these fragile molecular waves from any collision with air molecules or the faintest thermal vibration. Each successful test pushes the boundary further, proving that size alone is not the disqualifying factor. There is no magic number of atoms where quantum behavior suddenly stops. This points decisively toward the process of decoherence as the true border guard. Quantum behavior fades not because an object is big, but because big objects are incredibly difficult to isolate. They have more surfaces, more internal vibrations, more ways to interact with the stray photons and particles that fill even the best vacuum. Every interaction is a tiny measurement, entangling the object with its environment and bleeding away its quantum coherence. A single molecule in an ultra-high vacuum can maintain its superposition. That same molecule at room temperature, bombarded by air, would decohere in a fraction of a blink. The classical world emerges not from a fundamental change in the rules, but from the practical impossibility of keeping complex things perfectly isolated. So is our everyday reality just an approximation, a useful illusion born of constant interaction? The mathematics suggests yes. There is no separate set of classical laws written into the universe's code. Newton's equations for a flying baseball are an excellent, emergent description of the average behavior of trillions of quantum particles that have decohered into definite positions. The solidity of your desk, the predictable arc of a thrown ball, the unambiguous tick of a clock, all these are the products of decoherence on a massive scale. They are what quantum mechanics looks like when it has been averaged out by the relentless chatter of the environment. This leads to a profound and humbling possibility. There may be no fundamental quantum classical boundary at all. The entire universe, from the smallest quark to the largest galaxy cluster, may be fundamentally quantum. What we call the classical world is simply the quantum world viewed through a fog of constant interaction. We are not living in a separate realm. We are immersed in a giant, decohered quantum system. The chair you are sitting on is in a definite place not because it cannot be in superposition, but because it is continuously being measured and pinned down by the light in the room, the air, and even the cosmic microwave background radiation. Its quantum nature is still there, hidden beneath an avalanche of environmental noise. The quest to find this boundary, therefore, becomes a quest to quiet the noise. Every time scientists cool a larger object, trap it more perfectly, and witness its quantum behavior, they are not finding a limit. They are cleaning the window, revealing that the quantum reality extends much further into our world than we ever dreamed. The border is not a wall, but a horizon, receding as our technology and understanding grow. The very idea of motion without energy consumption sounds like a fantasy, a violation of the most sacred laws of physics. Yet in the quantum realm, such a state not only exists, it has been created. These are quantum time crystals, a bizarre and entirely new phase of matter that ticks forever in its ground state, the lowest energy configuration possible. Unlike a pendulum that needs a push or a clock that needs winding, a time crystal's motion is intrinsic, an eternal heartbeat woven into the fabric of its quantum structure. It achieves this by breaking a fundamental symmetry we take for granted, time translation symmetry. In an ordinary system, if you perform an experiment today or tomorrow, the laws of physics are the same. Time is uniform. A time crystal spontaneously breaks this symmetry. Its components undergo periodic motion, returning to their original arrangement not after any arbitrary time, but at a fixed, definite interval, creating a clock that is built into the matter itself. It is not a perpetual motion machine. It does not do work or output energy. Instead, it is a perfectly stable quantum system trapped in a non-equilibrium pattern that repeats indefinitely without friction or energy loss, a cosmic metronome set by quantum rules. The creation of the first time crystals in the laboratory was a triumph of quantum control. Scientists used chains of charged atoms, ions, held in place by electromagnetic traps and laser cooled to near absolute zero. By carefully applying a pulsed magnetic field, they could nudge the system into a state where the spins of the ions would flip in a precise, repeating sequence. Crucially, this flipping occurred at a period different from the pulse of the external drive. The time crystal had its own inherent rhythm, a quantum synchronization resistant to perturbations. Think of it like pushing a child on a swing. If you push at the natural frequency of the swing, it goes higher. But if you create a time crystal, it is like pushing the child at one rhythm, and the child swings back at a completely different, slower rhythm all its own, locked in a stubborn, stable beat against your efforts. This robustness is the key to its potential. In the noisy, decoherence-prone world of quantum technology, a time crystal's periodic order is protected by its very structure. This makes it a prime candidate for an ultra-stable quantum memory device. Imagine a qubit whose information is not stored in a fragile superposition of a single particle, but in the collective, ticking rhythm of an entire time crystal lattice. The information would be distributed and protected by the crystal's temporal order, potentially making it far more resistant to the environmental noise that plagues other quantum systems. It would be a memory that does not just hold data, but beats time to safeguard it. Beyond memory, time crystals open a portal to an entirely new frontier in quantum materials science. We have long classified matter by its spatial symmetry, how its atoms are arranged in space, leading to crystals like diamond or quartz. Time crystals introduce temporal order, a classification based on patterns in time. This suggests the possibility of entirely new phases of matter with exotic properties, materials that oscillate, pulse, or rotate in their ground state, offering new ways to control and manipulate quantum information. They represent a profound shift in our understanding of what matter can be, not just something that exists in space, but something that performs in time, a silent dance at the quantum level that may one day form the bedrock of a timeless technology. If matter can have a rhythm built into its very fabric, what about the stage it dances upon? The quantum world we have explored is a realm of discrete jumps, probabilistic outcomes, and observer-dependent realities. These are not just scientific curiosities, they are the operating parameters of our existence. And to some of the most provocative thinkers of our time, these parameters look less like fundamental laws of nature and more like the features of a very advanced computer program. This brings us to our final quantum mystery, one that bridges physics and philosophy, the simulation hypothesis. The idea is as audacious as it is ancient. What if our universe, with all its galaxies, life, and conscious experience, is not base reality, but a sophisticated simulation running on some unfathomable cosmic computer? While this sounds like science fiction, it has gained serious traction in recent years, not from mystics, but from quantum information theorists who point to the bizarre rules of quantum mechanics as potential evidence. They ask, if you were to design a universe from scratch in a simulation, what would the code look like? You would need to conserve processing power. You would not render every detail of every atom in real time. You would only calculate the properties of a system when it is being observed, when the information is needed. This is eerily reminiscent of the quantum measurement problem. The wave function, in this view, is not a physical field, but a set of unrendered possibilities. The act of observation is the trigger that forces the simulation to calculate a definite outcome, to collapse the wave function and generate a concrete reality. Much like a video game only renders the graphics in the player's field of view to save computational resources. The discrete, quantized nature of reality we have seen, from the energy levels of atoms to the possible granularity of space itself in loop quantum gravity, fits perfectly with a digital framework. In any simulation, there is a finite resolution, a pixel size, a smallest unit of information. Planck length and Planck time, the scales at which our physics breaks down, could represent the fundamental pixel size of the cosmic simulation, the limit of its rendering engine. Even the speed of light, the universe's ultimate speed limit, could be seen as a processor clock rate, a limit on how quickly information can be updated across the system. The holographic principle we discussed earlier, which suggests all the information in a volume of space is encoded on its boundary, is a dream scenario for a simulator. It is a data compression scheme of almost unimaginable efficiency, storing a three-dimensional world on a two-dimensional surface, exactly how we create holograms and virtual realities today. Perhaps the most striking glitch in the Matrix, however, is the role of the observer. In a purely physical, classical universe, consciousness should be an irrelevant side effect. Yet in quantum mechanics, the act of observation is inextricably linked to the actualization of reality. From the simulation perspective, this makes a strange kind of sense. Conscious observers are the users of the simulation. Their attention, their measurement, is what calls for the rendering of a consistent shared reality. The famous double-slit experiment, where the behavior of a particle changes based on whether it is watched, could be seen as a resource allocation protocol, only calculating a definite path when a user is looking. Proponents like philosopher Nick Bostrom have formalized this into a trilemma, arguing that at least one of three propositions must be true. 1. Almost all civilizations at our level go extinct before becoming technologically mature. 2. Almost all mature civilizations lose interest in creating ancestor simulations of their past. Or 3. We are almost certainly living in a simulation. If even a tiny fraction of advanced civilizations run such simulations, the number of simulated beings would vastly outnumber the beings in base reality, making it statistically more likely that we are among the simulated. This is not a claim that can be tested with our current science, and many physicists dismiss it as untestable and therefore unscientific. Yet, the hypothesis persists because it provides a startlingly coherent, if speculative, framework for the quantum weirdness that otherwise seems so alien. It reframes the deepest mysteries not as flaws in our understanding, but as clues to the nature of the substrate. Are the probabilities of quantum mechanics the result of a cosmic random number generator? Is quantum entanglement a form of non-local data linkage within the code? Is the apparent fine-tuning of physical constants, like the cosmological constant, simply the chosen settings for this particular run? To be clear, the simulation hypothesis is not a theory of physics. It is a modern metaphysical mystery, a narrative inspired by our most successful theories of information and computation. It forces a profound shift in perspective. For centuries, we have sought to understand the universe as a mechanism. Now, we must consider it as a computation. The quest to discover the laws of physics becomes, in this light, an effort to reverse engineer the source code of reality. Whether we are in a simulation or not, the exercise is invaluable. It pushes us to look at the quantum cracks in our universe not as bugs to be fixed, but as features to be understood, the subtle signatures of whatever reality, simulated or not, ultimately is. From the ghostly dance of superposition to the cosmic silence of dark energy, these 30 mysteries are not isolated puzzles. They are facets of a single, shimmering truth. Our classical intuition, built on a world of solid objects and predictable paths, has been chipped away piece by piece, revealing a foundation of probability, interconnection, and breathtaking strangeness. We have seen that particles are waves, that observation creates reality, and that empty space seethes with energy. We have followed threads of entanglement that stitch the cosmos together, peered into black holes that might be holograms, and questioned whether time itself is an illusion born from quantum correlation. Each mystery, from the humble double slit to the staggering multiverse, points toward a deeper layer of existence where our familiar concepts of space, time, and matter dissolve into something more fluid, more intelligent, and more wondrous. The grand, unifying quest running through them all is the search for quantum gravity, a theory that could weave these disparate threads into a single tapestry. It would tell us what space-time is made of, what happened at the Big Bang's first instant, and how the universe computes its own reality. This is not merely an academic exercise. It is humanity's attempt to read the source code of existence. The journey through these mysteries leaves us with a humbling and exhilarating realization. The universe is far weirder, more interconnected, and more magnificent than our ancestors or even our own childhood selves could have ever dreamed. The solid ground beneath our feet, the steady tick of the clock, the very notion of a separate self, these are comfortable illusions woven from a quantum fabric of unimaginable complexity. But this is not the end of the story. It is the opening chapter. The greatest discoveries lie ahead, waiting in the next experiment, the next equation, the next leap of imagination. So tell us in the comments which of these quantum mysteries completely rewired your understanding of reality. Was it the spooky action of entanglement, the holographic principle, or the haunting possibility that consciousness itself might play a role? Let us know, and if you want to keep exploring the cosmos's deepest secrets, be sure to subscribe. Our journey into the strange and beautiful heart of reality has only just begun.